Welcome everyone. In this program I will deal with overhauling the water pump and thermostats on my AC engine. Yes, I did say thermostats, plural. I'll explain about that later. My main focus is on the water pump, which was the Achilles heel of the post-war AC engines for its reliability. After World War II, AC updated their engine design, and this included a completely new water pump. They moved it to the side of the block, pumping coolant into the engine, and this allowed a lower bonnet line. The low position of this pump means that it can keep pumping even if the coolant level has dropped. On the downside, if it is the pump that is leaking, the leakage will continue. There is also the high static pressure on the low mounted pump, so leakage might occur when the engine is switched off. Perhaps the biggest detailed design problem was that the pulley is not aligned with the ball race bearing. Most car water pumps have a bell-shaped pulley so that these are well aligned. This problem creates turning moments on the shaft from the fan belt loading, resulting in side load on the rear bearing, which is a plain bearing. Another noticeable difference is in the design of the rotor that pumps the water. It doesn't resemble the typical centrifugal rotor that you might find in either a water pump or air compressor. There is one benefit to AC's design. In a typical rotor you get a pressure difference between the front and back, and it might have some small vents drilled through it to help equalise the pressure. This pressure difference would create an end thrust that the bearings have to deal with, so this problem doesn't apply to the AC. While this rotor might be inefficient, the AC's cooling system can function as a thermosiphon system. That is, coolant can circulate by convection without a pump because the radiator is quite tall relative to the engine. The pump is necessary to cope with the more demanding conditions. Leakage from the pump is something that owners might typically have to contend with. A tiny amount of leakage from the weep hole is normal as water lubricates the carbon seal. Over the years, some owners have modified their pump, some have changed the internals, some have fitted completely different pumps. However, there are things that you can do to minimise trouble. That is where this video comes into play. The pump is held onto the side of the block by 4 studs. It is plumbed into the bottom of the radiator and also the bypass hose. Opening the pump reveals the bronze rotor and the rear bearing inside the rear casing. When you remove the pulley and push the shaft out, the spring-loaded carbon seal can be seen. This runs against a bronze ring pressed tightly into the front casing. Back in the 1980s, I bought a complete repair kit, including a new shaft from AC at Thames Ditton. I made a tiny but important mistake. I had to transfer the brass drive peg for the seal to the new shaft. I did not get it in exactly evenly. One end poked out about 0.5 millimetre more than the other end. As a result, the carbon seal was binding against that drive peg. It's important that the seal can slide freely and evenly. There are also some small design deficiencies which are easy to improve. A modern version of a water pump seal would have the spring firmly connected to it. The ACs are separate and there is nothing to keep the spring concentric with the shaft. That same issue applies to the cup washer that the spring bears against. Both the washer and the spring can slip completely off centre, resulting in uneven pressure on the seal. There's a neoprene washer behind the seal, and I found that if you reverse the brass cup washer, it fits neatly over the neoprene washer. This contradicts the handbook drawings and the installation in my spare water pump. To keep the spring concentric with the shaft, I made a small neoprene washer to place inside the spring, but making sure that it does not obstruct the seal when it slides back on the shaft. Another detailed problem was how the rotor was fixed to the shaft. It was held with a mild steel drive pin, pinned over at each end. To facilitate this, the pinholes in the rotor are larger than the hole through the shaft, but this can lead to a slack fit, depending on how well it is installed. If it is slack, the spring will push the rotor against the rear casing, and the spring loading on the seal will be reduced. I decided to plug the 2 holes in the rotor by screwing in pieces of BA screws and then drill them at the same diameter as the hole in the shaft, which is 1/8 of an inch. I then installed a stainless steel split pin which I trimmed to length to maintain balance. The bronze plain bearing in the rear casing was still in good condition, having renewed it in the 1980s. Now we can turn our attention to the front end and the bearing and its oil seal. I installed a type of shaft oil seal that has an extra wiping lip for keeping out contamination. The seal is pushed into place from the front of the pump. Then the ball race bearing goes in. This must be the open type, so you can smear in suitable water pump grease. Then place the washer over it, followed by a felt washer soaked in oil. Cut out my own from a sheet of wool felt. Then the cover screws into place, and not forgetting the distance tube that goes between the bearing and the pulley, which you can see inside the felt washer. The pulley uses a split pin as its drive pin and is held by a central self-locking nut or a slotted nut when split pin. It is worth making sure the mating surfaces of the two casing halves match perfectly before making a paper gasket and using some liquid sealant to complete the joint. Also make sure that the outlet pipe flange mates correctly against the block. AC always recommended a very thin paper gasket here, but it will leak if the two sides are not parallel. You might need to fettle the two main mounting points to get this perfect. Since I have a spare pump that needs overhauling, I might see if I can add a second ball race bearing onto the front end and find a suitable bell-shaped pulley to fit. Turning our attention to the fan, this is mounted on a separate pulley with its own bearings. Mine showed nowhere. It's a good idea to paint the blades red for safety. Moving now to the engine thermostat, this is the old-fashioned bellows type. Assuming that the bellows are okay, then a slight issue might be the valve disc. These are screwed onto the rod and then soldered. Even if the solder looks sound, you might find that it is not fully closing, or it starts to open too soon. I have a spare thermostat that was slightly open when cold, so I experimented with it to see if I could adjust the disc to seat better. After melting the solder and unscrewing the disc, I removed the old solder, cleaned up the rod end and disc, and screwed the disc back on. I made sure it was fully closed, but only gently, and then resoldered. You can see that the AC's thermostat is rated at 78 degrees C, which is the temperature at which it is fully open. There is an alarming practice that I've seen recommended. Some people change their thermostats to one of a lower temperature rating from the original in an effort to reduce overheating. This won't cure overheating, although it might delay its onset. More worrying is that it increases the periods at which the cylinder walls are below the critical temperature that causes corrosive combustion products to condense. This causes upper cylinder wear. But this is one of those issues that can go unnoticed, and by the time the engine wears out prematurely, it is difficult to make the connection as to the cause, especially if there are multiple causes. I've also read claims from merchants that thermal efficiency will be altered by changes in coolant temperature. That's based on the amount of heat loss from the cylinders. This is a fallacy that the great Sir Harry Ricardo spent half his life trying to dispel, although it is far too complex to explain here. He published several textbooks if you're curious, but keep in mind that you have to work in absolute temperature scales to analyse energy losses. The real reason for changes in efficiency were due to other things such as the effect on carburation. The reason the AC's thermostat has that low rating of 78 degrees or 172 in Fahrenheit is that the AC's engine is not pressurised. Slightly more modern engines had pressurised systems to raise the boiling point. That permitted a higher temperature of the coolant, thus increasing the temperature difference between it and the air passing through the radiator. The thermostat can be tested in a pan of water over a stove. I should really have used a deeper pan, but did not have one. Therefore my thermostat was heating via its casing, but it was still possible to establish its characteristics by removing the heat source. It did indeed become fully open at 78 degrees C, with initial opening at roughly 55 degrees. And now to the mysterious second thermostat. These are often referred to generically as Otto switches, as some were made by the company of that name. This one was made by the British Thermostat Company Limited, who also made thermostats for Rolls-Royce Merlin aero engines. Its purpose is to switch off the auxiliary enrichment carburetor, often wrongly called an automatic choke. There is no choke. As you might expect, it switches off as the engine warms up. It is rated at only 35 degrees C, which might seem very low. However, it is not in direct contact with the coolant. It sits inside this thick aluminium casing, which acts as a heat sink or buffer. This delays the transmission of heat into the thermostat itself, by which time the coolant will have reached a higher temperature. The thick casing also delays the drop in temperature of the thermostat, so that it doesn't keep switching on and off. I tested mine over the stove inside the outer casing and kept water from entering the unit. Water at 70 degrees C took 30 seconds to cause the thermostat to open its switch. It closed again at 36 degrees C for water temperature. I'm sure I will revisit the cooling system in the future, but that is all for this watery adventure. Thanks for watching.